All right, and welcome to our faithful 5 viewers. It seems like we're losing viewers every day, or people just don't want to wake up early anymore. Getting used to VODs. Well, that's all right. If you do like VODs, please subscribe to our YouTube channel. Go and scroll down, click on the YouTube link, and then hit the subscribe button. We're trying to get to 100 subscriptions so that we can get our own custom URL. Good morning, Z1. I don't know who you are. If you use your name like Maddie did, I can actually refer to you and I know who you are. I just woke up like a minute ago. Nice. See, the cool thing is now you can literally just roll out of bed, turn on your laptop, and then be in physics class all of a sudden. So that's that. Alright, so today we're going to talk a little bit more about the electric field. Oh yeah, so the Streamlabs auto mod will, delete your messages if you do any excessive caps or try to post links or stuff like that. So yeah, good morning, good morning. Oh look, our follower count keeps on going up. Hey, there's Giorgio. All right. So anyway, we were talking about the electric field, so today we'll do a couple more conceptual questions, especially the first question and the next mastering physics, and then we'll just do a Flippy entry today, Flippy entry number 4, and that should be it. Remember, today is Wednesday, and it's a short day. How's the sound quality? I kind of changed this setup a little bit. Can you guys hear me fine? Is it too loud or too soft? Let me know in the chat. Ooh. You're all right. Thank you, Chris. Electric fields. All right. Hey, there's Victoria. Cool. Welcome. All right. So if we use the simulator that I showed you yesterday, it actually makes all of these questions really easy. So this is the first question on the third Mastering Physics number 3, Unit 9. And this one is due next Monday, which is the 23rd. So again, the idea is that even though I'm giving you like almost a week to do this, you want to get started as soon as possible. So for example, the one that was due yesterday, if you try to do it yesterday, you probably run into lots of issues. And not only that, you have no time to actually ask questions. Right? I want you to get started. I want you to see those questions. I want you to ask questions during our live streams now, so that you're ready with those questions. If you're trying to do it Thursday night and it's due at midnight, or it's Tuesday night and it's due at Tuesday midnight, then you're not going to have a very fun time. So yes, please start early. That way you can ask questions early. Hey, that's what I did. Very Wait, what did you do? As in start early, or you're talking about procrastinating? Well, anyway, you don't have to answer that. You can plead the fifth. Okay, well, you could answer it. Mastering Physics number 3 is due the 23rd, so our goal should be to do at least 1 or 2 problems today, and then a couple more tomorrow, and so on, and not wait until Monday to do them all. Okay, so let's take a look at question number 1, which says it's a electric field conceptual question. Electric field conceptual question. All right. So this is a question that you can do using the simulator, and it makes it really simple. Basically, they're giving you charges. So on a number line or on the x-axis. Okay, there are 2 charges. one is towards the left side in the negative area, and one on the right side in the positive area. Okay. And they are equidistant from this middle line. And they've divided the number line into 4 regions, basically your multiple choice. Oh, not 4, 5 regions, your multiple choice, meaning any point to the left side here is choice A. Right. Your dog is next to you, wants to learn physics. Nice. All right. So any point, if you think your the answer is anywhere to the left of the left charge, then you would choose A. And so if you think it is between the left charge and the origin, you would choose B. If you think it is at the origin, you would choose C. And then a little to the right would be D, and then all the way to the right would be E. So these are the choices. And so the question asks, where can you find the electric field, net electric field? So where is sigma E? Oops, my vector hat kind of messed up there. There we go. Sigma E is where is it equal to 0? Is the question. So where can we cancel out all the electric fields? Remember, electric field vectors, based on the type of charge you have, if you take a look at your pictures that you have, it comes out of the plus and then goes into the minus. But if you have 2 pluses, remember how at the middle, as long as they're equal charges, in the middle there's a vertical asymptote, and then the field lines kind of curve like so. Right? Instead of doing it this way, we can do this homework problem using our simulator. So we're going to use the same charge and field simulator. Okay, let's go and show the grid. I'm going to put 1 at -2 here. Oops. Okay, and then 1 over here. So you can sort of see how you have this vertical asymptote in the middle, and then the lines kind of curve and turn away. Okay, and essentially you can try to use this sensor, and the sensor showing values. The sensor will show you where electric field is 0. So right now it's at 31. So as you can see, if I move closer and closer to the center, the value drops to 0, somewhere around there. Okay, anywhere to the left starts increasing, anywhere to the right starts increasing. So somewhere around the middle, if I can get there, somewhere around 0. Okay, so that means that the answer choice is C. Ooh. Okay, let's do a couple more examples. And if you're with us, go ahead and log on to ClassFlow. Let's go to ClassFlow, and I will ask some ClassFlow questions. So I'm going to log into my ClassFlow. All right, and so we'll do some multiple choice. Let's see, connect your students. Do you guys remember the password? Here, I'll type it. Alright, so you want to go to classflow.com/student and type in the password. Ooh, continue. Yay, we have one person. Maddie, very good, Maddie. Leading the charge. QGX7X. Can I say no? No, Christian, no. You cannot. So it's just true or false. And so I'll do a couple more. Let's see. Okay, and if you don't know, that's all right. Just go ahead and use the simulator, and then you can play along. Oh, we lost one of our viewers. Great. So imagine now having different amount of charge. So I'm going to put 1, 2, -1, -2. We're going to put a +2 charge here. So 2q, remember q is the variable for charge. We don't know how much, but it's, it's 2 times whatever that is. Uh-oh. And then over here, we will put a -1q. -1q. Okay? So again, similar to the question on mastering physics, if you think it's over here, you put A, so where is this net electric field equal to 0? Okay, so if you think it's between the charge and the origin, it's B. If you think it's the origin again, it's C. If you think it's to the right of the origin, it's D. And if you think it's all the way over here, it's E. This one is slightly harder, so either model it or take your time. So multiple choice, A through E. Start poll. Here we have it. I'll hide the answers for now, so you can take a look at your class flow. But if you're not ready to answer, let's discuss how we got this answer C one more time. Okay. Oops. Okay. So remember, every electric field, what's the simulator called? It's called charges and fields. Charges and fields. Actually, I can just type in the link, so let me just link it on the chat. Set charges and fields. Q. My touchscreen on my laptop stopped working. Any advice? It might be one of your function keys. So if you hold Fn, look at all the F buttons. There's an icon that might turn it off or something. Or try turning on tablet mode. That might also work. I'm not sure. I would say consider going to the tech office, but sorry. Yeah, the old power on, power off trick might work. Alright, so anyway, anytime you have a charge, each charge has its own electric field. So let me use different colors. Let's say this orange positive charge. This orange positive charge will have its own electric field that point outwards from it. So over here it's going to go to the right. Over here it's going to go to the left. Okay. And so as you, oops, I drew it too big. And now as you go further and further out, the electric field gets weaker and weaker from that charge. Okay, we're not drawing the net electric field here. We are drawing the individual electric field. So let's go and call orange the electric field for number 1, E1. Next, we'll do green. Let's do green. So this green one, the charge on the right, that one also has its own electric field. I just closed my laptop and opened it. Now it works. Excellent. So this green one represents the electric field for the green charge. And again, since it's positive, it's going to point outwards. So outwards to the left, but then as it goes further left, it gets weaker and weaker and weaker. right? Here it's going to go to the right, but as you go further out, it's going to get weaker and weaker and weaker. Okay. All right. And now next, let's go and draw the net electric field. So we'll use purple. The net electric field is another way of saying sigma E. So the sum of all E's. The net electric field is the sum of all these vectors, the vectors from both the green and the orange. Okay? So notice how green points to the left and orange also points to the left. So the net electric field is to the left. Okay? Here we are slowly deleting or slowly decaying in that orange is trying to push to the right, but green is trying to push to the left. The closer you get to green, the stronger green becomes. And the weaker the orange becomes. So eventually the net electric field actually drops to 0. So you start off with a slightly stronger to the right, but that slightly stronger to the right starts to decrease, decay, gets weaker and weaker and weaker until it turns to 0 directly at the middle. To the right side of the origin, it'll point slightly to the left, but as you get closer and closer to the green, it'll be more and more left. Okay. Now on the right side of green, both the orange and the green point to the right, so they both point to the right. But again, as you get further and further out, it gets weaker and weaker and weaker. So the purple is the net electric field. And so by looking at the vectors individually, we add them up, we can see how at the center we have 0. Now in our question, the charges are different. One of them is stronger. So it's kind of like a beam struggle, a power struggle. Imagine, Goku and Vegeta, or Cell and Gohan Super Saiyajin 2. Yes. And they're struggling with their beam struggle, but of course one of them is stronger, and so one of them will win out. So instead of the tie being in the middle, it'll shift. The stronger one will kind of push it away or something like that. Let's take a look at our guesses, shall we? Whoa, look at our guesses. We have one person say it's B, 2 people say it's C. Okay, remember this question has different charges. Different. Oh, is it positive? Uh-oh. I put one positive and one negative. Oh boy, here we go. No, I don't. Only Dragon Ball Z, but Dragon Ball Z is different. Hint, it is not C. It is not. It can't be in the middle. Not only are the charges different, but the charges are opposite, which means attraction. They are attracting each other, right? So let's do the second one together, and then I'll close it up. So in the second one, we have a negative charge. I'll use blue for the negative one. It's -1, Q. And the positive one, let's use orange. Oh, I should have used same colors. Oh, okay. So green is positive, and orange is negative. -1Q, -2Q. I do. So there's nothing wrong with that. FR, what? What do you type in there, Chapito? Are you just rolling your face on the keyboard there? Is it positive? Oh yeah, you're right. Thank you for pointing that out. It is +2Q. Good. Okay. So, I mean, I gave you an option. You could have used the simulator and actually do it, or you could try to figure it out here using our vector model, right? Actually, we're going to do both. So Here we go. So orange, again, orange is a negative charge. So what do the electric fields look like around a negative charge? Can anyone answer that? Chat, what does the electric field look like around a negative charge? Hint, think of a black hole. Or a sinkhole. Or a manhole. Well, around a negative charge, yes, towards it. How is the delay? Is like, I thought it was like 3 seconds or something. But anyway, on the left side, it's going to point to the right, but on the right side, it's going to point to the left. But as I go further out, as you go further out, it gets weaker and weaker. So this is just for the orange. Remember, we're going to look at it one at a time. Yes, the green one is there, and then we will add them later on. So orange points towards the orange charge, but as you go further out, it's going to get weaker and weaker. Green is a positive charge. For positive charges, it points outwards, away from it. Now, when you're close to it, it's going to point away very strongly, away and away. Okay. But as I go further out, it's going to get weaker and weaker. So the arrows drop in size. Okay. As I go further out to the right, it's going to get weaker and weaker and weaker. Okay. And now we want to add the vectors up. Add the vectors up, so that's purple. So, okay. So here, remember, we have little tiny greens and big oranges to the right. So the net electric field will be something to the right, because the right will win. And as you get closer, it'll go bigger and bigger to the right. Okay. So this was choice A. And choice A points to the right. Definitely not a 0. Okay. Let's take a look between the origin and slightly to the right of the negative charge. Okay. Notice how both arrows point to the left. So we're going to get a left. That is definitely not 0. Okay. At the center here, notice how both both electric fields from each charge points to the left here, so it's also left. So it's definitely not C. This was B. This is C. Yeah. Are we changing our guesses now? Oh, look, our guesses are changing. Cool. Now we only have 6 people. Christian, Bryant, Dennis, Mads, Giorgio, Toria. And a couple of lurkers. Lurking. We have 5 lurkers. Lurking in the shadows. Alright. Here in choice D, look, the arrows both point to the left. And left will add up. Remember, in order to get 0, you need a left arrow and a right arrow to cancel each other out. So that's left. And then finally here we are much further away than the orange, and we're very close to the green, so that's right. Now it looks like we canceled all of our options. Oh no. Is it none of the above? But none of the above was not a choice. So now we have to think. Alright. Remember, we are assuming that the magnitudes are the same if we're going to draw the same sized arrows. If you have a charge that is slightly bigger, okay, that reinforces each arrow to make it slightly stronger than it would be if it were just 1 Q. Meaning, each green arrow is actually a little bigger, twice as big as I have drawn it before. Okay. And so if they're twice as big, that means that you can cancel it out if you are over here to the left of the orange charge. Whoa. All right. Now we can do it with variables or equations as well. Remember, E is equal to KQ over R squared. Okay? In order for the two electric fields to cancel each other out, E1, the magnitude of E1, must equal the magnitude of E2. Okay, this ratio. And the only way to get there is to be to the left of 2, because when you're towards the left side of 2, you get a green arrow that points left. And you want to be on the left side of the orange one, because if you're on the left side of the orange one, you get an orange arrow that points to the right. And not only that, you have to be further away from the positive 2 charge and closer to the negative 1. Basically, based on the fact that the radius is in the denominator, okay, as you increase the distance, you decrease the electric field. And because you have twice the charge on the 2q, okay, you have to be further away from the 2q but closer to the plus 1 in order for these arrows to cancel out. Okay. Whereas if you look at in section E, okay, the orange arrows are very tiny in comparison to the big giant green arrow. We get a big giant green arrow because the green charge is twice as big, 2 Qs. Okay? So there's no way for these little tiny orange arrows to cancel out the big giant green arrow. Right? So let's go and instead use the simulator to solve this problem. So simulators are great, and this is what you're going to be doing in the future. Just you simulate it, you hard code things, and then you simulate it. Oh look, one person got it. Oh, one person got A. So anyone actually use the simulator to answer the question? Or you just guessing? So we had a -1 on the left side, so let's go and do a -1 on the left side. Right? And we want 2 positives on the right side. So minus on the left, 2 positives on the right. Boom. I went offline. Are you sure? Stream. Bitrate is 4800. I'm still here. Can anyone see it? I think we're still good. It might be a Giorgio thing. Oh, it lagged for a sec. That is possible. All right. Well, anyway, notice how I put 2 charges. So let me start all over then. So we're using our simulator to answer the question instead. I put 1 negative charge here, and then let's go and put 2 positive charges here. 1, and then 2. So when you put 2, it kind of pushes it, and you can see how towards the right side of the 2 charge, you get arrows, and there's, and as you get closer, it's bigger and bigger. But notice how the arrows kind of disappear on the left side of the -1, right? It gets fainter and fainter. This is telling you that to the left side of this blue charge, you basically have 0. See? Oh, I found it. Where is it? No. Oh, I thought I saw a 0 somewhere. Somewhere. Nope. Somewhere here. but I can't do it. Oh well. Anyway, somewhere here on the left side, you see how you can get some sort of zero. Now it is true that if you are infinitely far away, then yes, the electric field is zero, but it's kind of difficult to be infinitely far away from everything. Make it an announcement on Canvas. But there's like a schedule at the top. It says 8 o'clock every day. Oh, yeah. I don't know how to actually do that. Let's see. There are announcements. It's just dashboard. I'll have to figure that one out then. I can do modules, import from comment, no. Collaboration, modules, quizzes, outcomes, files, pages, people, grades, discussions. I don't see it anywhere. Oh, assignment on Canvas. Oh, I misread it. I thought it said announcement. If you make it an assignment on Canvas. I see. I did. I think I did. It says 318 Flippy entry number 4, and I put it on your to-do list, so it should pop up in your to-do list. So I did that. Okay. All right, so the answer was A. You have to be to the left of the -1 charge. You want to be close to the -1, but far away from the +2. Far away from the +2. Yeah. So we're done with the notes part. We're just going to do Flippy entry number 4 now, and then we'll be done with the day. So go to your Flippy entry number 4. Flippy number 4. Flippy number 4. All right. So the title is called Electric Potential. Well, you're going to have to copy it down then you'll have it. Okay, so remember there's a top and a bot, so I'll just start with the top side. Yes, the flip book. So on the top side, we have some figures again. So top side is usually pictures. You want to divide the top side into 2 sections. So imagine this being the top side. Actually, I shouldn't do that. Undo. There. We'll start with figure 1. Figure 1. And we have a drawing. Basically 2 charges. Okay. So the idea is that if you have 2 charges that are the same charge, like plus and plus, we know that they would repel, but if you have a charge that is plus and minus, we know that it will attract. Like so. Okay. Let's say these 2 are separated by a distance of d. No, let's not use d. Let's use r. There we go. Stay consistent. Okay, so there is an electric force between them. There is an electric force F electric on the positive charge that pulls the positive charge down, and at the same time, Newton's third law, opposite and equal reactions. At the same time, the negative charge also experiences an electric force upwards, like so. And so this is naturally occurring. What we're going to do here now is that add an external force. If we don't return to in-class go for the rest, Esther, how would we turn it in? We would scan it and then take pictures one by one, turn it into like a document, and then submit it through Canvas. All right, so this is just naturally occurring based on the electric force. Okay, let's go ahead and apply a next or an applied force. So you physically using your powers to pull them apart. Naturally, the two charges want to get together and come closer and closer together due to the electrostatic force, but you're going to apply an external applied force, F applied, FA. And by doing this, you are forcing the charges to separate. And when you separate them, it takes energy, it takes work, it's hard. You can imagine there being like a spring between them, and the spring is trying to collapse and bring them together, whereas you are trying to stretch the spring out. So that's what you do when you try to separate two charges that are opposite in charge. So the energy that is required to do that is called the electric potential energy, PEE. And it's equal to K times Q1 times Q2 divided by single R. It's like the force equation, except there's a single R in the denominator. Okay? Basically, if you recall, energy is like work, and work is force times distance, and force is KQQ over R squared. So if I multiply KQQ over R squared, one of the R's goes away. Okay, so that's figure 1, and then to the right of it we'll draw figure 2. Figure 2 is slightly different. Let's imagine now having a giant row of positive charges, and we can do this by basically having a metal sheet and charging up the metal sheet. So plus, 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 plus. And then here at the bottom, we'll have a second metal sheet. And this metal sheet will put negative charges on. Minus, 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 minus. Okay? In order to get them to be positive and negative, what we have to do is actually connect them to a battery. Now, when we get to Unit 10, we'll actually learn how to write the circuit symbols, but for now we're actually going to draw a battery. So here's a battery. Remember, batteries have this little dimple thing at the top, and it's like a cylinder. Right? Can anyone tell us the side that has this little dimple thing? Is that the positive end or the negative end? Batteries. I'm sure you've used batteries before. Imagine this being like a AA battery. AA. Duracell, Energizer. Well, based on how I connected it, you can kind of guess. The top side must be positive, and the flat side is the negative. Okay, so by connecting little metal plates to a battery, we basically can make the metal plates themselves positive or negative charged. Okay. Now you have to connect two. You can't just do one. Let's go and separate these charge plates by a distance of d. Mm-hmm. And we know that the electric field, so let's use purple again, the electric field inside should be pointing away from the plus and towards the minus. Pew, pew. Now on the inside we have a uniform electric field. Right? So the purple is E, the electric field. Now E without the vector hat means energy. E with the vector hat is electric field. So those are two different things. I have PS4, I don't need batteries. Oh, well, wait a minute. Doesn't the PS4 have wireless controllers? Don't you have to charge those wireless controllers? What do you think is inside those wireless controllers, huh, buddy? Oh. Alright, so anyway. Got him. So by doing this, we can store energy, and the energy inside here, say the electric potential energy, is equal to QED, Q times E times D. Okay, this is assuming that there is a tiny Q inside here. Now Q could be plus or minus. I'm just going to draw plus for now. It could be any charge. Oh, that is true. I mean, you're not using a Duracell battery, I suppose. But if you wanted, you can take the battery out of your controller and then connect it to metal plates so you can have your own uniform electric field. Ooh. Alright, so a couple of things. Uniform electric field. Okay. It has the same spacing and lines, so the distance between my purple arrows has to be equal. Same spacing and lines. The spacing between the lines have to be equal. And then the direction has to be the same, of course. So same direction. Same magnitude. And also the spacing between the plates. So if the first one talks about the spacing between the lines. That's the distance from each purple line to purple line. When you draw it, you want to draw them equidistant from each other. That way it indicates that the electric field is nice and constant. Okay, this means that the electric field anywhere inside these two metal plates is constant, similar to how we say gravity is constant near the surface. The electric field is constant between these two plates. And you also want to maintain the distance d the same. So the separation distance has to be the same as well. Same spacing in D. Separation of plates. Okay. The AA battery gives us something called voltage. So we will write delta V in our battery. Okay. And do we know how many volts a AA battery is? How many volts? How many volts? Ooh. It is 1.5. Excellent, Dennis. 1.5. All right, that's the top side. Let's just go and write the stuff down on the bottom side, and then we'll be done for the day. So here's bot side. Bullet point number 1. Work done to separate charges. Work done to separate charges. Oops, I didn't spell it right. Separate charges. Actually, let me just type it. Can I just type it? Probably. Work done to separate charges become PEE becomes the electric potential energy. Ooh, it turned into P. Ooh, that's not what we want. We want PEE, electric potential energy. And this is a figure 1. The governor said he doesn't expect us to, yeah, he doesn't expect, there's no announcement made, but if there are no vaccines found in the next couple of weeks, then yeah, we're pretty much going to do the same thing. Delta PEE. Oh gosh, this is actually harder than I thought. Insert. Can I do symbols? Symbols. Is there a delta? Yay, there's delta. Actually, it's not too bad. Delta PEE is equal to QED in joules. So again, energy, of course, is measured in joules J. So if you're trying to solve problems, make sure you use units of joules. Okay. Let's finish up this Flippy book, and then after I end the stream, we can take questions and stuff. You guys are getting distracted here. I know it is important. I understand. But let me finish typing this, and then I can actually read your questions and try to answer them. P, QED in joules, J, and to get that, remember, delta PE, the change in the potential energy. So let me do another symbol delta. There we go. The change in potential energy is work, W, which is equal to force times distance, which is equal to, remember, force is charge times the electric field, and so charge times electric field times distance. So that's how we get this equation, all the way from unit 5. Oops. Electric potential. Now, there is another term called electric potential instead of potential energy. And the hardest part of the test is to make sure you read things carefully. Some of the questions say, what is the electric potential energy? Some will say, what is the electric potential without the word energy? So, so there's a small difference. The electric potential, and the symbol for that is V, capital V, is the energy turned into P again, divided by, gosh, is PEE divided by the charge Q. I should write V is potential energy per charge at a point in space. Okay, so the equation would be V is equal to PEE over Q. Which equals KQ divided by R. Single Q, single R. Potential difference, which is delta V, so remember difference is delta, is what we call voltage, is work per charge and is measured between 2 points in space. Okay. All right. So this would mean that delta V is equal to delta potential energy, the change in your potential energy, PEE, divided by Q, which is the same as work divided by Q. Okay. Potential difference is called voltage and is measured in volts V. Yeah. This is the only time where you're going to get a variable V, which is a variable in your equation, that has units also of V. All other variables have different letters for their units, but this is the only time where you're going to get volts, or voltage is measured in volts, the easiest one. Unfortunately, there aren't any other ones. Okay. And one thing to remember is that 1 volt is equal to 1 joule per coulomb. So these are units. I'll put them in parentheses. 1 volt is 1 joule per 1 coulomb, or 1 joule per coulomb. And the last bullet is potential difference over a uniform electric field, E, is equal to the potential difference over a uniform electric field, E, is defined as delta V equal to that E times D. And this is in figure 2. So only use this equation, delta V equals ED, if you know for a fact that the electric field is constant. It's uniform. So the question says, in a uniform electric field of 100 newtons per coulomb, and a separation distance, blah, 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 then you can just multiply and get the voltage. So this is called the VED equation, V equals ED, and it's good as long as the electric field is constant. I should add some tick marks and stuff, so let me do that. Draw. Okay. So bullet point here, bullet point here, bullet point here, here, here. Ooh, I don't like all these red things. How do I whatever. This is a vector. Now, even though E is a vector, we're actually using it as a magnitude when we do the VED equation, because it is just a constant value. But we know that E does have a direction, and E is pointing away from the positive and towards the negative. Okay. All right, so let's take a look. At the top, you should have these two pictures. The title is Electric Potential. We have figure 1, which is two charges. One's a positive charge, and the forces are applied from the center of mass. One's a negative charge. And in order to separate them, we're using an applied force, and that applied force does work on the system. And that work that you do gets stored in the electric field itself, so that when you let these two balls go, right, after stretching them out, when you let them go, they will accelerate towards each other and eventually, crash into each other. In figure 2, we have two plates. The plates are positive and negative. By connecting them to a battery, we can get them to be charged up. And by doing this, and with a separation distance of d, there's a uniform electric field inside the two plates. Okay. And if I put another charge in there, that charge will have a certain amount of potential energy equal to little q times the electric field that exists between the plates and the distance between the two plates. Okay. It is not how far q is. It is the distance between the two plates. Okay. All right. So here's the bottom side. You should just put all of this stuff in the bottom. And that should be it for today. All right. Well, thank you for watching. I'll see you tomorrow.